now, after understanding the van der Waals equation and its significance, now we are coming to a point where gases can be liquefied, which was not true for the ideal gases. At particular temperature and pressure, gas can be converted into liquid, and therefore we can say that real gases cannot behave as an ideal gas or a wide range of temperature and pressure. This was first explained by Thomas Andrew by considering carbon dioxide as a gas. He has plotted pressure versus volume for at a various temperature. So, at a particular temperature he plotted a graph. So, another he changed the temperature. He has done the experimental analysis and this graph is obtained, that is also called as Andrew's isotherm. So, this is the graph which represents the Andrew's isotherm. Now, if we observe the temperature, the higher temperature, the relation between pressure and volume is similar to that of the ideal gases. As the temperature goes on decreasing, now the relation is no longer become ideal and the graph is something different, abnormal. Even at low temperature, the relation between pressure and volume is more and more abnormal. For a carbon dioxide gas, if we consider a line which represents Tc, that is called the critical temperature. Now, what do you mean by critical temperature? It is a temperature at which a gas is converted into liquid even if the pressure is increased. So, that gas is called as, that temperature is called as critical temperature. And obviously, the pressure and volume, the corresponding pressure and volume are called as critical volume. Now, if we consider this graph at lower temperatures, we will be having a 3 different volumes at a particular temperature. But at a critical temperature, we have one volume and that is the critical volume. Now, to calculate critical temperature, critical volume and critical pressure, we can use van der Waals equation, and for that purpose we will be using molar volume. Okay. So, this is the graph that we have to use while solving this. Okay. So, from this graph one thing is clear, that V minus Vc is equal to 0, which means V is equal to Vc. So, if you see at lower temperature, there are more than one volume at particular pressure. At particular pressure, if you see the parallel line, at a very low temperature there is one parallel, the line become almost parallel. Before that, that line that is obtained during the experiment, that is called the metaphase. Again there is one curve after a particular volume. Okay. So, if we go on increasing the temperature, you will find at a particular temperature this is true, volume remain constant at a particular pressure, and that time the liquefaction start. So, I can say V minus Vc is equal to 0. Now, I will go to the van der Waals equation for 1 mole of a gas. So, P plus A upon V square into bracket V minus B is equal to RT. Now, since we are talking about 1 mole, this volume V becomes Vm, so that we call it as a molar volume. We can solve this. So, after solving, I will get PVm plus A upon Vm minus Pb minus AB upon Vm square, that is equal to RT. So, multiplying this equation by Vm square, so we have P Vm cube plus A Vm minus Pb Vm square minus AB is equal to RT Vm square. Okay. Now, by considering this relation, V minus Vc whole cube is equal to 0. Okay. So, this equation becomes V cube minus, so this V I will consider it as a molar volume. So, this becomes Vm cube minus 3 Vm square Vc, okay, plus 3 Vm Vc square minus Vc cube is equal to 0. Now, this equation if I simplify, just I will write in the similar fashion. So, I will get Pvm cube plus Avm minus Pbvm square minus AB minus RTVm square is equal to 0. Now, if we compare the things, now we can get the various relations. So, after comparing these two equations, we can write critical volume is equal to 3B, critical pressure therefore is equal to A upon 27 B square, and critical temperature is equal to 8 A upon 27 RB. So, the values of A and B can be used to determine the value of critical volume, critical pressure and critical temperature. Now, this is very important for considering the liquefaction of gases, real gases, and this includes everything. As I already told you, in an Andrews isotherm which has applied for carbon dioxide, this isotherm is valid for almost all real gases except hydrogen and helium. So, for that I already explained you, because the size is very small, the intermolecular forces of attraction are also weak. Okay. Now, some of the things which we need to remember here, we have to remember, and one is called as a Boyle's temperature. The temperature at which real gas behave as an ideal gas is called as Boyle's temperature. So, that we have to remember. Now, all those formulas were derived. There is one called as a Goldberg's assumption or Goldberg's law, and according to Goldberg's law, according to the Goldberg's statement or Goldberg's assumption, boiling point of a liquid is equal to 2/3 of critical temperature. So, these things we have to remember. Now, there are certain things which have already mentioned in a notes or in a various book about the liquid state also, which consists of vapor pressure, surface tension and viscosity. These are the three properties we have to study. Vapor pressure is important for us, and that we are going to use in a solutions and colligative properties chapter. While viscosity and surface tension are more related with the physics. So, there will be a chapter properties of fluid. There you are going to study in detail. In this chapter, we are going to emphasize more on gaseous properties and gas laws. So, here we are coming to the end of the theory part. Now, as we have not discussed anything about the real gases, we have not solved any problem based on real gases and the van der Waals equation. So, that will solve in the next session. Thank you.